Adaptive task management, enabling multi-site workflows with Globus Compute. This is effectively this new scheduling load balancing system that we built on top of Globus Compute to enable multi-site workflows. Hugh meme. Basically, the supposition that I'm making here is that kind of at these different levels of hierarchy, we see very similar patterns. We have slow memory, fast memory, vectorized operations, serial operations, and network capability, storage, et cetera. So why don't we realize this at the larger scale? You know, we see this on the core level, the processor level, the system level, but we can also have these very advanced networks like ESNet in this case, and different systems that specialize in different things. So we have this system ATM, Adaptive Task Management, that effectively tries to go after this point. This is entirely client-based, so you don't have to worry about deploying any custom Globus Compute endpoints, which I know some folks have done in the past. But this just makes it easy. You can use all your same endpoints, and effectively the scheduling is just done locally on your laptop. Ultimately, is this super scalable? For the most part, yes. We'll show that in a second. But again, this just makes it extensible, easy, compact, and most importantly, reusing of existing infrastructure. We can dig into the specifics later if we have more time. Effectively, what this stack of algorithm is doing is we add a monitoring layer around each task that effectively records things like timing information. We also can include things like utilization or power consumption, basically whatever you can get from a system level call from within Python. So you can't have anything that has elevated permissions. But if you can access it via a Globus Compute task, then we can add that into our monitoring, records all that, and then effectively all we're doing is balancing the pressures across all of these different endpoints that you have access to with respect to these multidimensional costs like memory pressure or service units or time. We have a task handler that we've implemented that incorporates dynamic endpoint shaping. So this is using the Globus multi-user endpoints. I talked a little bit about this last year when this was more in its infancy. But effectively what this is that users are inherently very bad at estimating kind of what level of parallelism their workflows have for the most part. And so we want to be able to kind of dynamically shape the packing of these different tasks on endpoints just by very simply launching different numbers of tasks to each endpoint. We don't see crazy speedups. It's usually mid-single-digit percentages, but when you're trying to squeeze out extra performance, you know, you'll take 6%. Best papers have been written on less. The actual task scheduling, like I said, is really just balancing these different pressures of these multidimensional costs that we're optimizing for. We can do this both with batch tasks as well as DAG-based scheduling. Effectively, the only difference is that with DAG-based scheduling, we have a conception of a queue because you may be loading multiple individual tasks to an endpoint. So this is more like traditional scheduling problem rather than just doing this kind of global load balancing, filling in the low spots. So super simple results just to show you kind of what this is supposed to do. These are our 4 different workstations that are sitting right over in that office right there. And really all this is showing is if we're running many matrix multiplications, can we effectively load balance properly? The interesting thing here is we actually were running too many matrix multiplications, so network bandwidth started to become a problem. But that's, you know, toy example. The interesting example is many of you have probably heard of NSF Access. This, I guess you could call it a consortium of all these different computing sites where people are donating or providing their resources through Access, where you have this conception of a credit. And a credit is a very ambiguous thing because it means something different to all the computing sites. And I know some of those sites are here, so I won't badmouth any specific sites. But basically, you can have a different number of core hours, different amount of performance per credit on all these different machines, ranging from, I think the best one that we saw over the course of this work was 10 or 12 core hours per credit, all the way down to about 1/8 of a core hour per credit. Now, of course, these fancy Intel Xeons might be a little bit newer or whatever, but there's definitely a nonlinear difference of credit exchange. So we want to be able to take these multidimensional costs. So you heard Logan talk a little bit earlier, 15 minutes ago, about this ML in the loop materials design. So I don't need to rehash that. That's our use case for this. And so actually running on these NSF access resources, taking into account both cost and time, we ran only on 4 systems because that's all we had available to us to get concurrently via, or not via, but because of waiting too long in queues. Again, not looking at any computing site in particular. But effectively, what we're showing here is that we can do 2 things. One, we are finding new materials more quickly. Batch time is going down. And the really cool thing about this result is right around that batch 7 point, we stop using expanse. Hopefully no SDSC people in the audience, just because queue times were too long. And so it became prohibitively too expensive to execute tasks on that resource. So we do see a slight bump in batch time, which is bad. But over the course of the next 3 rounds, we do see that improve now that we're not using expanse anymore. So we basically go from 4 to 3 systems and are able to load balance well enough that that doesn't really matter too much. We did a simulation across all of the access machines. Basically what this is showing is initially we go really, really fast, but then we start to trade off that time for these compute credits. We scaled up to 16,000 endpoints, 16,000 tasks on a laptop, so it's scalable to be client-side software. In summary, this is basically a load balancer. We can talk more about it. Very quick, wait, there's more, because I know I'm at 0 minutes. One thing that kind of enabled this is what I call Globus Compute Wormhole, which is basically just a Globus Compute wrapper for Magic Wormhole. Made it really easy to transfer files. Coming soon to a GitHub near you, because I know that would be useful to people. So with that, I'll take questions.